Hello everybody and welcome back to another data science video with me, Ryan. Today we're going to be talking about local outlier factor. Local outlier factor, which is another concept which I think is quite poorly explained online. So I'm going to do my best to make it simple and easy to understand. Simple and easy to understand. It's going to be clearly explained. So let's dive in. So what is local outlier factor? Local outlier factor is a density-based outlier detection metric. What does that mean? It means that it takes into account the density of the neighborhood of a point when considering whether it is an outlier. In this case, we take into account the density of the points here and here, and maybe a third closest, which might be that one or that one, when we consider whether this point is an outlier. So what we are essentially doing is comparing how close these points are to their neighbors compared to how close this point is to its neighbor. Now that's a summary, and that's not what the formula is going to wind up doing, but that's a decent enough way of thinking about it, okay? So we're going to compare how close this point is to its neighbors as compared to how close this point is to its neighbors, and also how close this point is to its neighbors, and we're going to look at the ratio of this closeness to those closenesses. Okay, that's what we're going to do. That's local outlier factor. Local outlier factor. Now, local outlier factor has three steps. Okay, so step one, really simple. We find. I'm gonna type because it probably makes more sense. So step one is just calculate the reachability matrix, which is really simple. It's a really simple calculation, and I'll take you through an example of that. Okay. Number two is calculate the local reachability density of each point. So we have this thing called reachability. Reachability is just used to take into consideration points that have a lot of points really close to them. And I will show you kind of what that means in a moment. Then we're going to calculate the local reachability densities for each point. So going down here, that is how dense each one of these points is relative to each other. Well, by taking into consideration the points that are nearby. So by considering how close this point is to its three nearest neighbors, and then how close this point is to its three nearest neighbors, and how close this point is to its three nearest neighbors, or maybe that one. So we calculate the density, and it's a score 1 for each point. 1 for each point. So each of these points will have a local reachability density. A local reachability density for each point. Okay, once we've calculated the local reachability density, calculate the ARLRD, right, which is just the reciprocal of your local outlier factor. So we can essentially immediately calculate local outlier factor. And this is, just to know what ARLRD stands for, that's average relative local reachability density. But you know, think of it however you want. It's just convenient for my mind to have the formula in this form. So we're going to go through these steps. I'm going to rewrite these ugly looking formulae in a way that makes sense and a way that we can use them. And it's going to be clearly explained. So let's go. So our first step, like I just said above, is to calculate the reachability distance. And what that means is that if we're calculating the distance, say, from 1 to 3, okay, we will take the maximum of the distance from point 1 to point 3, or the k neighborhood distance of point 3, because we're going in this direction. The k neighborhood distance of point 3. Okay, so let me say that again. We are going to take the maximum of the distance between point 1 and point 3, or the k neighborhood distance of point 3. Now let's look at the k neighborhood distance of point 3. That's the maximum of its distance to its two nearest neighbors. So in this case, I've just circled the neighborhood there, which is points 2 and 5. So in this case, let's say that 5 is further away than 2 from point 3. And our other option is 1 to 3. Okay? So I want you to take the max of those two values. And clearly in this case, it's just the distance from 1 to 3. So here, distance 1 to 3, it's going to stay the same. It's going to stay the same here. Okay, so that value is going to remain the same. Distance 1 to 3, that value is going to stay the same. All right, let's take a slightly different example of reachability distance. So let's look at point 2. And I want you to get the reachability distance of point 4 to point 2. So from point 4 to point 2, from point 4 to point 2. And the directionality here is really important. The directionality is really important because the way that we calculate this affects which neighborhood we use to calculate the closest distance. Okay, we're taking the maximum of either the distance between 4 to 2 or the neighborhood of the destination point. That is the neighborhood of point 2. So in this case, we're taking the maximum of the distance of point 4 to 2 or the maximum of the neighborhood distance for point 2. In this case, I'm going to say that the distance from 4 to 2 is less than the maximum distance in the neighborhood of 2. Trying to draw a circle there. But assuming that the radius of that is actually a circle, we can see that the distance from point 2 to point 3 is greater than the distance from point 4 to point 2. And therefore, the neighborhood distance of point 2 is greater than the distance of point 4 to point 2, which means that our reachability distance for point 4 to point 2 is actually going to be equal to the distance from point 2 to point 3. And we're going to substitute that value in for this value, which means that when we look here at point 4, and we're going from point 4 to point 2, we're going to substitute this value here for that value. We're going to replace it. Okay? Now all this is doing is a little bit of pre-processing on your distance matrix, and it's going to let you just get a better metric when we perform the local outlier factor. Now, mechanistically, what does this mean? It means that you're going to go down the columns of your distance matrix. You're going to go down the columns of your distance matrix, and you're going to replace the second smallest value, the smallest value with the second smallest value. So let's look here. And when I say if you had k in your neighborhood, you would replace the n minus 1 smallest values with the kth smallest value, right? So you would replace the k minus 1 smallest values with the kth smallest value. So if in this case we had k equals 3, we would look for the third smallest value, which is this one, and we would replace this one and this one with that value, and we would leave this value the same. That's if we had k equals 3. Similarly, if we had k equals 4, which is moot because it's just the largest value, but we would replace all 1, 2, 3 of these values with the smallest. That's what it means mechanistically. This is what it means in terms of the drawing. So we're going to look here, and we're going to replace this value with that one. Similarly, we're going to replace this value with this one. We're going to replace this value with this one. And we're going to replace this value with that one. And we're going to replace this value with this one. Now, something that I want to note here, and this is important, is that before you do all these replacements, you need to make sure that you're aware of the two nearest neighbors of a given point. Now, they're highlighted here quite conveniently, but what I want to make sure is that as you go across the rows, that is from point 1 to point 2 and point 1 to point 5, you're getting the two nearest neighbors for each point. So point 1 to point 3 and point 1 to point 4, and also point 3 to point 2 and point 3 to point 5, point 4 to point 3. So these are the nearest neighbors, the two nearest neighbors of each of these points. And you go across the rows to achieve that. You go across the rows to find all those points. Now I'm highlighting them here because we need to keep these indices. We need to keep these indices of the two nearest points because our relative distance calculation can change what the two nearest neighbors are. And we need to keep the correct index of these values so that later when we perform our further calculations, we know which points are the neighborhood, are the k nearest neighborhood. Right, so like we said before, you go through and you replace this value with that value. You replace this value with this value. You replace this value with this value. And you replace this value with that value, and all I'm doing is going through the columns and I'm replacing the n minus 1 smallest values with the nth smallest value. And in this case I'm using n equals k, but n is the size of the neighborhood. Now that's just mechanistically, it's the same thing as what we did over here. And I might as well finish this off, so we're going to replace that one with that one. Now notice that okay, let's find an example, and I'm pretty sure there is one here. In P2, we've now got 284 in this position. So this value has been replaced with 284, 0284. Actually, let's just show. So here, so you've replaced this value with 284. Previously, it was 143, right? So this used to be 143. Because it was the smallest value. Okay, but if I were to take the two nearest neighbors now of point 2 going along the row, if I were to take the two nearest neighbors now going along the row, I would have found that this point and this point are the two nearest neighbors. That's wrong. You can't do that. You need to remember the indices of the two nearest neighbors of these points. Otherwise, you'll mess it up. Okay? So just remember the two indices of the two nearest points, or which those 2 points are, before we perform that calculation, and you'll be all good. All right, so now we've got the reachability matrix. The reachability matrix. So what we need now is to calculate the local reachability density. The local reachability density. That's our second step. Local reachability density. Second step. That's what we're going to do now. So our local reachability density, and I'm just going to try and pull up some formulas to make things a little easier. Actually, I already had it, but that's fine. It's this guy. Now, I hate mathematical notation. I just hate it. It's the worst. So let's work through what this actually means. So LRD of point X is equal to, and I'm just going to do it in code because I'm a data scientist and that's how I work, equals the sum of reachability distance of X to Y for Y in K neighborhood. That's the first row. Okay. Now I'm gonna keep my formatting a little bit wacky, but bear with me. That's all divided by len kn, right? And then all of this is to the power of -1. All of this is to the power of -1. So -1. Okay? So all that's telling you is that we take the sum of the reachability distances for a given point within its k-neighborhood, and we divide that by the length of the k-neighborhood and take the power of -1. So what is that? So for point number 1, we take the sum of this point and this point. We divide it by 2, power of -1. Right? Really simple. So that equals 0.234, plus 0.235, all of that divided by 2, all of that to the power of -1. Okay? So this is why I said we need to keep track of those indices, and I think it's helpful to highlight your k nearest neighborhood when you do your reachability matrix. You may not be given a reachability matrix in your exam. It may not be forever handy, but it's just a nice way to have the information available to you. Okay, so what? Now we can do this for all of our points. And indeed, I have some calculations for us to check with, which are here. Okay, so now we can crack out our little calculators and just check that what I said there is correct. And I'm just going to do it on my calculator now, and I'm sorry that that's off screen, guys. I could probably do it on Wolfram. Okay, so let me copy this into our good friend Wolfram Alpha. 4.2643, and there we go, 0.4.2643. So now you can go through each of these. So you can go 0.220 plus 0.284396. Okay, 0.194 and 0.235, 0.235, that's this guy, 24662, okay, etc. So these are our values here. That's your local reachability density. Local reachability density. So now we've calculated local reachability densities for each of these points, and I personally prefer having these in a slightly codey sort of way, just because these sums of these formulas don't really ring a bell to me. Okay, final step. Calculate ARLRD, which is just the reciprocal of local outlier factor. Local outlier factor. So this is it. This is it. Local ARLRD. We're nearly there. Step 3. Really simple. So we take the local reachability density of the point that we want to calculate the local outlier factor for, and we divide it by the sum of the local reachability densities of its neighborhood, and divide that by the length of its neighborhood, the number of values in that neighborhood. Okay, so it's kind of like an average, or you're comparing the local reachability density of a given point to the average of its neighborhood. In fact, that's precisely what you're doing for the ARLRD. And that's why this ARLRD, the average relative local reachability density, is a little bit handy, because it gives you a better way of thinking about the local outlier factor than does LOF itself, right? Because all we're doing is calculating the average relative local reachability density. That's the next step. And anyone can calculate an average, right? Like you know how averages work. You just go, okay, well, I've got the local reachability density for all the points, and all I'm going to do is calculate the local reachability density for all the points in a given point's neighborhood, right? So this point, for example, we just calculate it for these 2 points. Take the average, you take that point divided by the average, happy days, right? Average relative local reachability density. So average local reachability density relative. ARLRD. ARLRD. average relative local reachability density. Okay, it doesn't really sing that well, does it? But that's okay. Okay, so now let's look here. So for point 1, the 2 points that are in our neighborhood are P2 and P5. Okay, so for point 1, we want P2 and P5, and we also need the local reachability density of point 1, which is this one. So let's calculate that one. So it's going to be 4.264 divided by 3.968 plus 4.396. Okay? Now remember that you have to divide this whole thing by the length of the neighborhood, which equals 2. Let's stick this in our friend Wolfram Alpha again. I love Wolfram Alpha, it's so good. And I might just type this up in syntax, just so that I am happy with it. So we're going to do 4.264, right, divided by bracket, 3.968 plus 4.396 bracket divided by 2 bracket. And that is your ARLRD for that value. And then there's my Wolfram, there it is, 1.019. 1.019. Ah, did you know that you can get OneNote to do math for you? That's spectacular. Wow, I had no idea. So, let's compare that to our little outcome matrix, which I have prepared. Okay, 102. Okay, so now we can do this for other points. So let's say that we want to do 2. So let's look at our thing. So for point 2, your 2 nearest neighbors are... I would love to be able to draw OneNote. So for point 2, your 2 nearest neighbors are points 0, 220. Sorry, are points 3 and point 4. And I'm just looking at this highlighting to get those. But point 3 and point 4 are the 2 nearest neighbors of point 2. Okay, so point 3 and point 4, which means point 3 and point 4. Okay, and we also need the density of point 2. So what we get is 3.968, 4.662, 4.184, all of that divided by 2, and equals 0.8971. And what does our answer think? Perfect. Okay. Now you know how to calculate average relative local reachability density. And it is just the comparison of a local reachability density to the average reachability density in the neighborhood. Right? Don't forget what we're doing up here. You're just comparing the reachability density of a given point to that in its neighborhood. And just recall that you don't count that given point in its neighborhood. Okay, final step. We're nearly there. Thank you for sticking through this. We just calculate the LOF. And you know what LOF is? It's the reciprocal of ARD. Ready? One on all that. .1147. That's it. Okay, now you have the local outlier factor. You now have the local outlier factor. And you can do that for all of these points simply by following these 3 steps. Calculate the reachability matrix. Remember that you are doing the maximum comparing the distance to the destination's neighborhood. The destination's neighborhood. Okay? Which means that you go down the columns and you replace the n-1 smallest values with the nth smallest value. In this case, we replace the second smallest value, or the smallest value with the second smallest, etc. That's what we do in our columns. Remember that you keep the indices of your nearest neighbors for each point in each of the rows, and I find it handy to highlight those. Then, once we've replaced those values, as we see here, you replace your second smallest value in each of the columns with the smallest value with the second smallest value. Then we calculate the local reachability density, which is just the sum of the reachability distance for each of the points in the neighborhood, okay? And you divide that by the length of the neighborhood and you power of -1. Now that is, again, the local reachability density is just a way of checking how dense the values are in that neighborhood. Okay, reachability distance, so it's just the sum of the reachability distance for y in the neighborhood divided by the length of the neighborhood. So it's the average reachability distance of the neighborhood, the reachability distance of the neighborhood, and then one on that. Yes. Finally, we find the average relative local reachability density, which is just your it's just the average reachability density, and you divide your current reachability density by that, and then it's 1 on that to get your local outlier factor. So it's just a couple of averages, guys. Like, that's all it is. Local reachability density is just the average reachability distance in the neighborhood, and the ARLRD is just the comparison of your density to the average density in the neighborhood. So really what we should be calling it is right? It's 2 averages. That's it. Thanks, everyone.